So far, we have gone our merry way designing our little amplifier circuits and dependent source circuits and things like that, making several assumptions about the nature of operational amplifiers. Specifically, we have assumed that we have an ideal operational amplifier. Among other things, this means that, if you recall our little ideal operational amplifier equivalent circuit, that the input impedance is infinite, meaning there's no current into either of the inputs, that the output impedance is zero, meaning that no matter what we connect to that as a load, that it does not affect the output voltage. There's no internal drop across an internal resistance. And also we have assumed that the value A, the actual amplification, is infinite. Now, there is no operational amplifier that meets all of these qualifications. Some come very, very close, but in some very demanding situations, you may need to take these non-ideal characteristics into account. Very often we deal with this simply by selecting a better operational amplifier, one that has a higher input impedance, for example. But sometimes you actually have to design your circuit in such a way to account for the non-ideal characteristics of the op-amp if there's simply not one that's good enough to meet the specifications. However, before we start all that, we need to look at a generic negative feedback amplifier. This is a block diagram of a generalized negative feedback amplifier. Now, several things of note about this. First of all, there's some input voltage, V sub I. There's an output voltage, V sub O. There is a gain block called A. Now, this is where we would put our operational amplifier. A is the thing we have been assuming all this time to be infinite, which it really is not. And A has a name, and that is called the open loop gain. In other words, this is the gain of the amplifier stage without putting it in the loop. If you just sit the op-amp there by itself and hook it up, no feedback of any form, that's going to be its gain, A. Now, there's also another box labeled beta, and beta is called the feedback ratio. The purpose of this box is to take the output voltage, take some fraction thereof, and subtract it from the input voltage V sub I. Now, coming out of the box beta is some voltage V sub F, which goes into a little negative sign in that little circle. The little circle is basically an addition symbol. Note that VI comes in with a positive, VF goes in with a negative, and out of that little circle comes something labeled V sub E, and V sub E is simply V sub I minus V sub F. V sub E is called the error voltage. Now, this perhaps is a little bit of a misnomer because it's not an error in the sense that there's something wrong with this. This is simply the voltage that you get there if A is not infinite. As A approaches infinity, V sub E approaches zero. And so in some form or fashion, V sub E is related to how far away from infinity A really is. In other words, how poor your gain is. The smaller your gain, the bigger V sub E is going to be. Now, the term beta is normally less than 1. All of the examples that we have seen, beta has been determined by a simple resistive network, and so the amount of VO that is fed back into the inverting input has got to be less than unity gain. So beta is normally less than 1. However, there's nothing about this block diagram that says we could not put some sort of an amplification in that lower box so that beta was really greater than 1. We may see an example or two later in this course where we actually have a beta, a feedback ratio greater than 1. Now, with this structure, and again, this is a generic structure. This applies to any type of negative feedback amplifier, or at least almost any type. It doesn't mean you have to have an operational amplifier in the box labeled A. You could simply have a transistor there. You could have all sorts of things that could give you some amplification. In our case, however, this is almost always going to be an operational amplifier. If you analyze the overall gain in this circuit, V out over V in, which itself has a name, the closed loop gain, because that's the total gain of the entire circuit, including the amplification and the feedback and all of that, V out over V in, the closed loop gain, which we will indicate by A sub CL. If you go through the analysis, and I'm not going to do that here, it's in the book, you can follow it, it's not particularly difficult, but you end up with a final result that for any negative feedback amplifier represented in this form, that the closed loop gain ACL equals the ideal gain. In other words, the gain that we've been talking about all along, assuming that we have an ideal operational amplifier in our circuit. The ideal gain divided by 1 plus 1 over A times beta. Now, when you're analyzing situations like this, the term A beta pops up quite frequently, and it's convenient to give that term, A beta, a name, and that's called the loop gain. It's simply the product of the main gain stage times the gain, quote gain, it may be less than 1, of the feedback element. So that's called the loop gain, A beta. Now this is a fairly important result, and it makes a lot of things fairly easy to figure out without having to analyze individual situations every time. So closed loop gain equals ideal gain divided by 1 plus 1 over the loop gain. And we will see that again in the next video.